Hello everyone. Yes, this is take 2. Take 1 did not take. All right. So what are we doing? This is the agenda. For the first part of the video, I will work on hypothesis testing about a single parameter. Follow that up with confidence intervals. In part 2 of the video, we will work on hypothesis testing about a linear combo or a linear combination of parameters, and follow that up with hypothesis testing about multiple linear restrictions. Let's start from the top. Under item 1, I will do steps for doing a t-test, and I will show you under that the one-sided test and the two-sided test, and then there'll be more to know. Of course, there'll be p-values of t-tests. We will compare practical or economic significance versus statistical significance of a coefficient or an estimated coefficient. Ready? I am. Okay. Like I said, take 2. This better work. Okay. From the classical linear model assumptions, right, you'll have to refer to the end of chapter 3 and the beginning of chapter 4 for that. We can write this ratio here, where the estimated beta hat j minus beta hat, the real or the true beta hat, divided by the standard error of beta hat j, follows the t distribution with degrees of freedom n minus k minus 1. Now, you should have questions for me, although I can't hear you. Is a t distribution different from the normal distribution? In a way, the t distribution, as you can see on my drawing to the right-hand side, top right-hand side, the t distribution is the black line. It's shorter and it has fatter tails or thicker tails. Now, as your sample size gets bigger, the t distribution converges to the normal distribution, which has thinner tails and taller or skinnier. Right? They are both sort of bell-shaped curves, right? Okay. So, the first thing that you need to know about hypothesis testing is we need to state the null hypothesis. We need to state the baseline. And what is the baseline? Well, in this case, H0, the null hypothesis, is written as beta j equals 0. Now, 0, yeah, in this particular case, we are assuming that my pencil is okay. Good. In this particular case, when we write beta j equals 0, we go back to the econometric model. Y equals beta 0 plus beta 1 x1 plus ... plus beta j xj plus ... beta k xk plus u. If in the hypothesis we're assuming that beta j equals 0, that means that xj and y are not correlated, or we are saying that there is no effect of xj on y in the baseline. Now, we follow this null hypothesis up with an alternative hypothesis. The alternative hypothesis is what we are trying to show with our data. If we are trying to show that, there is a positive relationship between xj and y, then in your alternative, you better write beta j greater than 0. In the alternative hypothesis, such as here, beta j greater than 0 would mean that we are trying to use the data to prove that the relationship between xj and y is a positive one. Now, if we were trying to prove that that relationship were negative, then beta j less than 0 will be the alternative hypothesis that we state. If we are just trying to show that there is some relationship between xj and y, then we have to write beta j not equal to 0. And so the one-tailed test is where we have beta j greater than 0 or beta j less than 0 to use the data to prove that that exists. Otherwise, we have a two-tailed test where we are just using the data to prove that there is some relationship between x, j, and y. Okay, let's go back. The t-test. The t-test features the t statistic or the t-ratio. After you state your null hypothesis and your alternative hypothesis, you need to calculate the t-test or the t-ratio. This will help us test the hypothesis. So, if in the null hypothesis we hypothesized that beta j was equal to 0, then in our t-test we have to subtract 0 from beta hat j, the estimated coefficient. Now I do have examples coming up, so don't be discouraged at this point. And then you divide that by standard error of beta hat j. You should ask me a question. Why? Why do we divide by standard error? Here is why. I'll use an example to explain why. What if I told you I was going to give you money? I was going to give you 1,000. I'll give you money, 1,000. You should say 1,000 what? Yeah. Because if I just say I'll give you money 1,000, it doesn't make any sense. It's not, you need a meaningful metric to understand what I'm trying to give you. So if I said I'll give you 1,000 Korean won, for those of you who know the conversion rates, that's about 65 cents, right? That's in dollars. That's $0.65. Now, for my international audience, $0.65 cannot buy you a cup of coffee at Starbucks. Okay? Now if I do say that I'm going to give you, instead of 1,000 Korean won, I will give you $1,000. Okay. You see, now that makes sense because you understand what that 1,000 mean and what it will do for you. It's the same thing here. We divide beta, when we take beta hat and we subtract 0, it could, the value could be 2, 10, 40. Okay, but we want to do more with that value, and so we divide by standard error of beta hat j to see where in the distribution this difference falls. Where in the t distribution this difference falls. So, okay, that's how we get our t ratio or t statistic for beta hat j. And so what's the interpretation? Well, the t statistic or the t ratio measures how many standard deviations the estimated coefficient is away from the hypothesized value. In this case, the hypothesized value is 0. All right. What is the point of all of this? The objective is we are going to define a rejection rule, right? Like we calculate the test statistic and we see where it falls. Maybe some standard deviations away from the hypothesized value. So what, right? So what? Well, that's where our objective comes in. We want to define a rejection region so that if it is true, then H naught or the null hypothesis is rejected only with a small probability. Yeah, we are not women, right? Women, as a matter, before you get me cancelled or I get myself cancelled, women are right all the time. That's a fact. You take that fact from this woman. But on a serious note, we are economists and we are wrong sometimes. What if we reject the null hypothesis when it is true? Okay, we want to do that with a probability of only 5%, so that our confidence level is, 100 minus 5%, 95%. That's good, right? Okay. So from the top, right, to do a t-test, you state the null hypothesis, you state the alternative hypothesis, and then you calculate the t-test. I just showed you how to. You take your estimated coefficient, you subtract the hypothesized value, and divide that by the standard error, because we want to put this into some meaningful metric that we understand. Are we done? No. We are going to compare our calculated test statistic to some critical value. What is that critical value? Oh, that critical value is very much connected to your significance level. The error allowance that you have imposed upon yourself is connected to that critical value. Very interesting, isn't it? So how do you find the critical value? There are two ingredients that you're going to need. One, you will need the degrees of freedom, n minus k minus 1, and you'll need the level of significance, the error allowance we are imposing upon ourselves, which is 5%. Now, for those of you who are just joining us from the YouTube streets and are wondering what in the world is degrees of freedom n minus k minus 1, I will answer you with an example. When you play video games, you have maybe 5 lives. The goal in that video game maybe is to rescue some princess in a tower. So you're going to talk to the troll, you lose a life. You fall in the lake, you lose a life. Now you have 5 minus 2 lives left. That's your degrees of freedom. So as we calculate coefficients, the slope coefficient, the intercept coefficient, the intercept, we are losing life, quote unquote. And so n minus k minus 1 is the remaining life that we have in this game. Do you see? Okay, good. If you have other questions, please put them in the comment section. Otherwise, office hours or my email. So with these two ingredients, we find the associated critical value in a t-table. I will show you how to do that. I will show you right now, in fact, how to do that. If you had a degree of freedom of 28 and you had the significance level 5%, right? 5% significance level for a one tail is right here. So we are dealing with this column. You see that? We are dealing with this column. All right. And degree of freedom is 28. Degree of freedom is 28. 28 is right here, this row. And they intersect right there. So we have picked out the critical value, 1.701. That's how to pick them out. Let's go back. So I just showed you how to pick up a critical value in the t-table. And then we draw the associated graph of the rejection region. And I'll go back. So now that you have this 1.701, how do you draw the rejection region? Because, that will depend on the type of alternative hypothesis you have. If your alternative hypothesis is such that, the null hypothesis you had H naught beta J is equal to 0, right? We all remember that. Now, the alternative HA, A for alternative, HA is beta J greater than 0. Okay, That means that when you draw your t distribution or your t curve, your t distribution curve, which is what you see right here to your left, that critical value you just found is connected to the significance level. Yes, wasn't it one of the ingredients we used to find the significance level? Indeed, it was. And so when we draw it, we have that 1.701 demarcating the rejection region. And this rejection region is shaded in blue, and that area of the rejection region is equal to 5%. Beautiful, isn't it? Now, for those wondering, okay, where did this distribution curve pop out of? And how is that different from the table we just saw? They are not different. They are not different. The distribution curve is just the graph version of the table. And so the table is like the shorthand of the curve with values, so you can pick values out of it, right? Yeah. Now, if you look at the table carefully, you will notice that the degrees of freedom are quite small, right? The degrees of freedom towards the top are quite small. Yeah. So this is we use this when our sample sizes are small. Now, of course, you have AI these days. You could tell AI your degree of freedom, and you could tell AI your significance level, and it will spit out a critical value. Well, you also have to tell AI if you're doing a one-sided or a two-sided, and it will spit out your critical value. Beautiful, isn't it? All right. Let's go back. So, all right, we have done all of this, found the critical value, drawn the associated graph, demarcated that rejection region using both the significance level and the critical value. We've done all that. What's next? Well, you compare your calculated test statistic to that critical value. If your test statistic is bigger than the critical value, you reject the null hypothesis. Otherwise, you fail to reject the null hypothesis. And so that's the decision rule you have to make. Do the comparison and say whether you reject or fail to reject. And then you write a conclusion. I wrote a generic conclusion here for those who are interested to learn how to write these conclusions so they sound nice, right? I wrote a conclusion here that may interest you. So you can pause the video here and take a look at it. But I'm going to move on. We already talked about this. I do need to mention that the choice of the significance level is somewhat arbitrary, but it may also depend on the field. In economics, we have the 5%, the 1%, the 5%, the 10%, the 20%. At least these four, well, 1%, 5%, and 10% are super popular. There's the 15% and the 20% too. We just worked on this. Now here's a nice example. Okay, so we have log wage equal all that. I'm not going to repeat what they all are, but you can see it. What is happening? This is the wage equation. We are testing whether after controlling for education and tenure, higher work experience leads to higher hourly wages. We want to test whether the variable tenure and log of wages are positively correlated. We want to test whether tenure positively impacts wages. And so what's your H0? Well, your H0 will be, well, here they wrote H1. Your H1 will be the beta on experience is positive, and in the null equal to 0. 0 where we are saying there is no effect, right? And that's the baseline we are working with, and we are going to use the data to test if there is a positive relationship. Okay, so that's the first thing. We state the null and the alternative hypothesis. So we are working with this higher work experience. This is the one we're working on. Higher work experience. We're testing whether experience and wages have a positive relationship. I'm telling you, when I'm in that zone, ooh. Okay, pardon me for that. We are testing whether experience and wages are positively correlated. So as experience increases, does wage increase too? And so we have our beta experience equals 0 for the null and beta experience greater than 0 for the alternative hypothesis. All right. We need to calculate the test statistic. Now, before I move on to that next slide, which values are we using? Well, we are using our beta hat. Our beta hat on experience is 0.0041, right? So we will take our 0.0041 and divide minus 0 and divide that by 0.0017, the standard error, that one. Okay, and so that's what we have here. Our answer is 2.41. That's the test statistic. Now we are going to compare that calculated test statistic to a critical value. What is the critical value? Well, we used two significance levels in this example. The significance level 0.055% and the significance level 1%. And then we have the degrees of freedom, which is equal to 522. And so the critical values that we found that have been found for us, 1.645 and 2.326. Okay, so to these two critical values, we are going to compare our calculated test statistic 2.41. And what do we find? Okay, 2.41 is bigger than 1.64. Rejects the null. Yes. 2.41 is bigger than 2.326, slightly bigger, but we still reject the null hypothesis. Well, in the first part, with a confidence level of 95%, and in the second one with a confidence level of 99%. And so look at my conclusion. Compared to the critical values of 1.645 and 2.326, the calculated t-statistic of 2.41 is larger. So we reject the null that there is no linear relationship between experience and log wage. There is, in fact, a statistically significant relationship, which is why we are rejecting the null. Thus, we conclude that the coefficient on experience is statistically significant at the 95% and the 99% confidence levels, respectively. You see how beautiful that sounds? Yeah, you should learn how to write like that. Very good. Very good. Okay. So let's go back to the agenda. What did we just do? We just worked on a one-sided test, right? Where we saw the greater than 0, 1. Now we're going to work on another one-sided test for the less than 0, 1. So that's where we're going. So less than 0. Less than 0, the distribution graph that you draw, well, the distribution that you draw, the t-curve that you draw will look like this. With degrees of freedom 18 and 5% significance level, your critical value is going to be negative 1.734. Negative, yeah, because this is the other side. Less than 0. Less than 0 is negative, isn't it? Yeah. So we will reject the null if the t-statistic that we find falls in the rejection region is even more negative than 1.734. And this is how I found 1.734 in the table. If you notice, there's no negative values in the table. Yeah, there isn't any negative values in the table. But then I add a negative sign because it's a left-sided, right? It's on the left side, not on the right side. so I add a negative. My beta j in the alternative is less than 0, so I have to put the negative sign in there. Okay, so with a degrees of freedom 18 is right here, and a significance level of 5%, that's this column, right? I see where they intersect, and that's my 1.734 critical value. Okay. Now I put this in here. The t distribution is symmetric, right? It's around 0. So you're seeing the positive numbers in here. So knowing that the one-sided is on the left side, your 1.734 that you take from the table, you have to put a negative sign to it. So let's see an example where we do a left tail alternative test, right? So in the null, we have beta enroll equals 0. In the alternative, we have beta enroll less than 0. What is this all about? We are testing whether smaller school sizes lead to better student performance. So we are testing whether, and as enrollment increases, do math test scores fall, right? We're testing whether there's a negative relationship between these two. As enrollment increases, do math scores fall, and is that significant, right? So there we go. Do larger schools hamper student performance, or is there no such effect? So in the null, we are saying there is no such effect. In the alternative, we are saying, oh, there may be a negative relationship, and we are going to use our data to test for that. Very good. So we calculate the t-test using the estimated coefficient 0.00020, divide that by 0.00022, right? And so our t-test, the t-test is small, negative 0.91. Now, I'm not saying it's small because it's negative. Take the absolute value of that. It's 0.91. It's a small value, right? Okay. I should be giving you some ideas here. That the closer your t is to 0, and the bigger your standard error, the chances you're going to reject the null is low. And that's what we see here. You see, so we have the degree of freedom, and within our significance levels, we chose two significance levels here. One is the 5%, the other is the 15%, and we have their associated critical values there as well, and they are all in the negative as they should be. Now, if you don't work well with negative values, here is where I tell you, you have to draw this up, right? So let me try and draw this up. How about we draw them down here? So this one, whoops. How about we draw them down here? Let's use black, right? We draw them down here. So here we have the critical value 0.15 equal to negative 1.04, and here we have the critical value. Let's use a different color so it pops differently on your end. And in blue we have critical value 0.05 equal negative 1.65. Okay, and so I will draw it on the left side, isn't it? So something like this. Very good. And using the critical value, I find my shaded 5%, and that's associated with the critical value negative 1.65, right? Negative 1.65. Okay, now in black, I'm going to draw that something similar, but for this other side. This is negative 1.04, and let me shade that up. Okay, the rejection region is what I have shaded. The unshaded region is where we fail to reject the null. All right. So in red now. The calculated t statistic is negative 0.91. So let's put negative 0.9. Let's locate negative 0.91. Oh, it's here. This is negative 0.91. And here. Oh, look at that. Negative 0.91. Didn't it fall in the fail to reject H0 region? Yeah, it did. So in the region where we have the 0.91, this is where we fail to reject H0, right? Fail to reject H0. And in the shaded region, that's where we reject H0. Okay. Right, so it's good you draw this. When you draw this, it's easier to tell what is happening than trying to work all of this in your head. Some people can't do that, but for those who are just starting, please draw it. Right, draw it. Okay, the decision is we fail to reject the null because, well, negative 0.91 falls in the fail to reject H0 region. Okay, what's the conclusion here? I have the conclusion down there. Pause the video and read it to yourself. But what it says that is that based on the two critical values that we have, the t-test is much smaller, and so it falls in the fail to reject region, and so we reject the null hypothesis, or so we fail to reject the null hypothesis of no effect between school size and student performance in math. So we conclude that the coefficient on school size is statistically insignificant at the 95% and 85% confidence levels respectively. This is some very interesting stuff. Cool. Prior to this example we just went through, right? Like going back to that first example on the left tail, you can see that we have enrollment here without the log. What if we log the enrollment? How does that change things? When we use a different specification on functional form, level log here instead of level earlier on, does that change anything? Well, the R squared is slightly larger, 0.065, so about 6.5% in R squared. What was it before? It was 5.4% earlier on. So yeah, when you use the log, things may change, right? Things may change. And so when we use the log of enrollment instead of just enrollment as in the variables, the t-test, right, the t-ratio, the test statistic changes. It gets bigger. It gets bigger in absolute value. It was 0.91 earlier on. It's now 1.87 in absolute value. And so when we compare that to the critical value, 1.65, right? So the new one, I have green. Let's use a different color, green. How about that? The new one is 1.87, negative 1.87, right? Negative 1.87 is here, and negative 1.87 is here, right? So now, what is this green? This green stuff is where we used log enrollment, right? Used log enrollment in the data instead of just ordinary enrollment, right? When we did that, then we could reject our null hypothesis. And how large is the effect? Well, negative 1.29 was that, but if we are going to use, since we are using the level log, we have to take that negative 1.29 divided by 100 in order to give a good interpretation, right? Or in order to interpret, not to give a good interpretation, but in order to interpret it, we have to take our beta, negative 1.29, divide by 100, get negative 0.0129, and say for every 1% increase in enrollment, math scores will fall by 0.0129%, or for every 10% increase in enrollment, math scores fall by 0.129%. You see, and that is statistically significant at the 95% confidence level. Okay, now the two-sided test. With the two-sided test, our significance level is still 5%. So we take the 5%, and if we are doing this manually, we take the 5% and divide it into the two tails. So each tail has 0.025 or 2.5%. So where do we reject? We have two rejection regions. So if our calculated test statistic falls within the rejection region, then we can reject H naught. We can reject the null. So let's look at some. I believe I have a couple of examples coming up. Let's look at the first one. College GPA is regressed on high school GPA, ACT scores, and lectures missed per week. Right? So we are using the 1% significance level. From that and the degree of freedom, we found our critical value to be 2.58. So I'm working on the first bit here. So that is the T statistic for GPA, for high school GPA. That is 4.38. And how did we calculate this 4.38? Well, you take the coefficient on high school GPA and you divide by the standard error of high school GPA, right? Quickly put that in your calculator and see if you get 4.38. Now it is 0.412 minus 0 divided by, so how do we get to this? 0.412 minus 0 divided by 0.094. That's how we got it. Okay. And so we found out that our test statistic is greater than 2.58. Now you can pause the video here and draw it for yourself to see if that's true. Now on the bottom, skipped classes or skipped lectures, right? Now that's a two-sided test. How do I know that? It's the absolute. It's how I know that. And how do we calculate this? Well, we take the negative 0.083 divided by 0.0286. And we found out that that was also greater than the critical value 2.58 at the 1% significance level. And so for high school GPA and skipped lectures, the effect of that on college GPA was statistically significantly different from 0. It looks like they are all two-sided tests. Yeah, they should all be, since that's what we're working on. They should all be. Now, for this middle one, you can see that the calculated t statistic is less than the critical value at 10%. And so for that one, the effect of ACT scores on college GPA was not statistically significantly different from 0. And that it wasn't at the 10% significance level. So we compare the calculated test statistic to 1.645 for a significance level at 10% to 1.96 for a significance level at 5% and 2.576 to the one at 1%, to the significance level at 1%. Right, and this is happening if the numbers, the number of degrees of freedom or degrees of freedom is large enough so that the normal approximation applies. Now, if you go to the table, you will notice what that means. Let's go back to the table. See, so they are picking all of this from the table. From the table, you have this last but one row, right? This last but one row. 5%, yeah, there we go. When you have two tails, right? When you have your two tails, and it's the 5%, right? And you go all the way down, do you see that now you're no longer dealing with a t, but a z critical value? Do you see that? Hopefully you remember your statistics, and hopefully I'm remembering it right too. So anyway, your z will be 1.96, and that will be the 95% confidence level. Otherwise, if we are dealing with 10% significance level or a confidence level of 90%, then your z is 1.645. If you're dealing with a 1% significance level or a 99% confidence level, then your z is 2.576. So again, in the beginning, I'm going to go back to that slide just so we are all on the same page. In the beginning, I was telling you about the t distribution, and I said that the t distribution converges to the normal distribution as your sample size gets larger and larger and larger. That's what's happening. So as the sample size gets larger, your t distribution is converging to the normal distribution, right, or the standard normal distribution, which is what the table that I showed you here, the last two rows of the table is saying. Now, of course, the last row is showing you the confidence levels, but you see what I mean. The last but one row, that's what it is showing, that as your sample sizes get bigger, the t distribution that you saw up here converges to the standard normal. And in words, we have it written here. Normal approximation applies as the degrees of freedom get larger, or as your sample size gets larger. Degrees of freedom is sample size minus k minus 1. So in a way saying the same thing. So this slide should help you understand why I made a big deal of saying that in the null hypothesis, we have beta j equals the hypothesized value of the coefficient, which the hypothesized value can be 0. It can be 1, it can be 2, it can be some value, some other value, right? But this is what it is. So far, we have been subtracting 0 from the estimated coefficient in order to calculate the test statistic. Here is an example where the hypothesized value is not 0. So we are considering an interesting hypothesis whether crime increases by 1% if enrollment increases by 1%. So we use the log. The log allows us to say for every 1% increase in enrollment, for every 1% increase in enrollment, crime increases by 1.27%. It allows us to have that interpretation. Now, we want to check if for every 1% increase in enrollment, crime also increases by 1%. And so in the null hypothesis, H naught will be written as beta on log enrollment equal 1, and in the alternative not equal to 1. Do you see? So we don't always write 0. So how do we calculate the t statistic? Well, it's the 1.27 minus 1 divided by the standard error 0.11, right? And that is 2.47. Now, we do use a critical value here. The critical value is at the significance level 0.05, and degrees of freedom is 97 minus 1, so 98. 96. 97 minus 1 is 96. Okay. And so we compare our calculated t statistic 2.45 to 1.985, and we see that it's larger. So if you are to draw this up, and I encourage you to pause the video and do that drawing on your own, you'll find out that we do reject the null hypothesis here. Okay, so we've made our way down here to the additional things that we need to know about p-values. I need you to remember that the p-value of the critical value is the significance level. Remember, to find the critical value, we needed the significance level and degrees of freedom. The significance level and the degrees of freedom allows us to find a critical value. And when we draw that, the area to the left of that critical value, that shaded area, that was the significance level. That's the p-value. That's the area under the curve bounded on one side by the critical value. So the p-value of the critical value is the significance level. Now, our p-values reported for every, so if we calculate our coefficient and it comes with a standard error, and we can have a t ratio, a test statistic, can we also have a p-value connected to that? Yes, we can. If you take this R output, for example, this R output is the one where we regressed price on square feet and bedrooms using some data from Wooldridge's data collection, right? This is the estimate. This is our beta hat 0, our beta hat 1, and our beta had 2 beneath it. And then look at the associated standard errors. So this is like it is a grid. It is a grid. And so the t value here, how about I change? The t value here, let's do the one for square feet, circled in blue, right, is calculated as 0.12844. And that was too big, so let's get rid of it. Okay, let's try this again. 0.12844 minus 0, all divided by the standard error. You guessed it, 0.01382. And that's how we got our 9.291. Now look at the p-value next to it in green. So I'll change my color to green now and circle the p-value next to it. That p-value, that p-value is 1.39 e to the negative 14. That means you take the decimal point and move it to the left 14 times. So that's 0.000000000. You get the point, right? Okay, good. That p-value is really small. Which tells you what? Which tells you you will reject the null hypothesis that there is no effect of square feet on price here. You will reject the null. Now, I can draw this for us. Let me draw it for us, right? So how about I put some space? Insert space. Okay. Assuming this is your shaded area, and I'm going to do it not super precisely, but I'm going to do it so that it makes sense for everything that we are trying to do in a two-sided test. This is the shaded region in which your critical value, so plus critical value, and here minus critical value. Now, when the p-value connected to one of your coefficients is super small, that means it sort of sits here, right? So this is your calculated t ratio or test statistic. Right, it sort of sits here so that the area to the right of it is really small. So the area I have tried to shade in red, you can see it's tiny. We are saying that as your p-values get smaller and smaller and smaller, the chances you will reject H0 is higher. The opposite of that is when the p-value is bigger, the chances you will reject H0 is small, right? Okay, so that's why up here I wrote small p-value of t ratio. Small p-value of t ratio implies that the chances you will reject H0 is higher or could be higher. And for a large p-value of a t-ratio, the chances you will reject h0 could be smaller. You see? All right. And we can move on. We can move on to other things. What's the difference between economic or practical significance and statistical significance, and are they saying the same thing? Not really. They are not really saying the same thing. Practical and economic importance of an estimate that you calculate, that's measured by the sign and the magnitude of your coefficient. The sign of your coefficient and the size of your coefficient will give us some practical and economic significance of it, or will point to some practical or economic significance. So in this example, or in this output here, where you have square feet and bedrooms as the explanatory variables and price is the response variable, we expect a positive relationship between price and square feet. We expect a positive relationship between price and bedrooms. And so if the estimate on square feet has a negative sign, we should be worried that there is something wrong. And if the coefficient on bedrooms has a negative sign, we should be worried. Right here, they are both positive signs, so we are not worried. Right? Now, statistical significance, we check that when we do hypothesis tests. But they are not the same. The coefficient of a variable may have the wrong sign and yet be statistically significant. That could be because the model is misspecified. That could be a misspecified model, meaning maybe there are other explanatory variables that should be in here that are not. So we have omitted some variables, and so we are looking at a super biased estimate on all the estimators. Yeah. Now for a variable that has a statistically insignificant coefficient, can we drop the variable? When it comes to dropping variables, you want to look at the size of your of the sample. I will say it's better to report results with and without the insignificant variables, right? And be careful when you're doing that. So if the sample size is small, the effects might already be imprecisely estimated. So dropping the insignificant variables is not a strong case. So yeah, after you put your data into the statistical softwares and you get the output, you still need to make sense of the values that are in there, right? Is there a practical or economic significance of the coefficients in terms of their sign and magnitude? And then you check statistical significance too. Then you look at your sample size. If we got a bigger sample size and we got more explanatory variables, how would these estimates change? Right? These are things you want to think about and write about. Okay, based on our lineup, this is the second thing we are going to do, and then I will quit the video and do part 2. Okay, confidence intervals. We are going to manipulate theorem 4.2 and we'll see how confidence intervals are related to the two-sided hypothesis test. Basically, if the hypothesized value is not in the interval, we reject the null. Okay, so from theorem 4.2, I repeated up here for convenience. And so we have beta hat j minus base j divided by standard error of beta j and we are saying that follows the t distribution. So how do we manipulate this? Well, if you notice, the standard error is multiplied by the critical value, and on one side all that is subtracted from the estimated beta, and on the other side all that is added to the estimated beta, right? So that's how it was manipulated. And since this critical value, well, can it change? Of course it can change. It can change based on the significance level. So for a significance level of 5%, that is our confidence level of 95%, right? Now, what are these bounds? The bounds are random. Now, if we did repeated sampling, what it means for this interval, if we did repeated sampling, meaning I have a population of data, I take a small sample out of that, calculate my beta 1, my beta 2, my beta 3, all the way to all the bases, beta k, right? And I also calculated confidence intervals, right? What we are saying is, if you did that kind of repeated sampling, the interval that is constructed will cover the population coefficient, the true coefficient, in 95% of the cases. And so, well, at a 99% confidence level, your significance level is 1%. At the 95%, your significance level is 5%. And at the 90%, your significance level is 10%. So what is the lower bound? The lower bound is, it says so right there. That is the lower bound. And the upper bound is this other one in green. This is the upper bound. All right. And we are showing that the true falls somewhere between them, and that you see that in repeated sampling, such that the true beta is covered by the confidence interval in 95% of the cases. Now, the relationship between the confidence intervals and hypothesis test is, if the hypothesized value is not in the interval, we reject H0. We reject the null hypothesis. So here's an example. Two examples actually. One for log sales or annual sales, and the other one for profit as a percent of sales. Okay, so we have the one for the log sales on here, right? And the other one, how about I change the color? So that let's make that blue, so it's easy to differentiate them. Right, this is the one, the blue one, and that is the green one. This belongs to the green one, right? So it's easy to follow. Okay, so annual sales, right? We are constructing a 95% confidence interval. How do I know? I know because the critical value shows that there is a 5% significance level there, right? And the critical value we found is 2.045. So we take the critical value and multiply it by the standard error of the coefficient on annual sales, and then we add and subtract on the left side the estimated coefficient, 1.084, and then we find our lower bound and our upper bound. Our lower bound is 0.961, upper bound 1.21. Now, what is the null hypothesis and the alternative hypothesis that go with this? Well, it's beta on sales equal 0, and that beta on sales, log sales, not equal to 0. You see, so is 0 in this interval that I have covered in surrounded with green ink? No, and so we reject H naught. Do you see how this goes? Right. So the effect of sales on R&D spending is precisely estimated as the interval is narrow. However, 0 does not fall within the interval. So we are 95% confident that, right, the true is covered in is captured in there. The true beta is captured in there. Okay. Now the blue one. The blue one, so this is the beta for profit. All right, just P equals 0. Beta subscript P equals 0. Beta subscript P not equal to 0. Is there a 0 in this interval? Yes. There's 0 in this interval, so we fail to reject H naught. So that means that it is not statistically significant. This interval is wide, or is wider than it should be. To reject H naught, we need narrower intervals, and we want 0 to not be in the interval. You see? Okay. Now, some caution, right? A word of caution. Your 95% confidence interval is only as good as the underlying assumptions you use to construct it. So if you have any omitted variable issues there, well, first of all your coefficients are biased, but the coefficient estimates will not be reliable, and the OLS estimates are all biased. If there is heteroscedasticity present, then the standard error is not valid. You would need to construct a heteroscedasticity robust standard error. That is coming in future lectures, right? Anyway, if you have these problems, then your confidence interval that you calculated, your 95% confidence interval that you calculated, is not truly a 95% confidence interval. It's probably smaller, right? I mean, your confidence should be smaller. Cool. I'll stop here. I said I was going to keep it under an hour. I hope it's